computer science, the questions about how things behave or how things think goes all the way back to Leibniz, who considered about expanding a thinking machine until it was the size of a mill, so that we could walk inside and analyze it. More recently, however, Alan Turing proposed a way for us to consider what constitutes an intelligent machine. In the Turing test, we have a single person in front of a terminal who types back and forth IM style between two entities. One of them is a machine, and the other one is another human. So Turing argues that a machine is intelligent once it can successfully fool this human into thinking that it is this person more than 50% of the time. This does seem like a well-grounded way for us to establish a way to communicate and see an intelligent being behind a machine. But studies since then have not been very effective at implementing this. For example, ELIZA is a program known as a chatterbot that attempts to emulate communication. This is a talk that I had with one built into Emacs for this presentation. And you'll notice that as fun as it doesn't really seem to be going anywhere. Every year, the Loebner Prize is a competition held to determine if someone can create a machine that is capable of passing the Turing test. But unfortunately, Marvin Minsky, a well-known artificial intelligence researcher and perhaps founder in the field, calls it obnoxious and stupid. Even in the field, all the sorts of products of the Turing test are railed against. So another thought experiment that's pertinent to computer science is John Searle's Chinese room. Imagine that you have a machine that is capable of receiving Chinese input and giving out Chinese output in perfectly understandable manners. And so it would appear to be intelligent. But imagine instead that we put a human on the inside who does not understand any Chinese but has a book that is able to map input to output. And so with no understanding, is unable to, we can see that the mechanism within it doesn't actually understand. And yet we see that it does, that it can behave normally. And so it's kind of like our mechanical Turk here, where we have something that appears to be working, but just human on the inside. Two common arguments we see against this is that one, from Cohen, is a lack of specificity from this thought experiment. The thought experiment takes a long time in the actual text to explain the content of it, which makes it weak in that it isn't definitive. Many people have come with many counter-arguments that twist the way this is presented. Another issue with it is that comes against it is feasibility.
10 minutes.
This comes primarily from an argument of more scientific people like those in physics, who say that the reason why this isn't an okay thought experiment is because it is unfeasible to determine. Just very similarly, Stephen Harnett argued that it took us forever to figure out how to design a chess-playing computer that could actually defeat a human, such as Deep Blue against Kasparov. So this sort of argument comes to look at the distance between these two audiences, that we have a very philosophical argument that is not able to generate any sort of excitement within another crowd. So given the apparent lack of progress, I guess the one last thing I should note is that computer science is built upon a thought experiment. Alan Turing also developed the idea of a universal machine, a thought experiment that drives much of how we consider computer science today. So clearly, the context for a particular problem matters significantly in its resolution, as his was a very mathematical one. And so the value of thought experiments in computer science exists. But by expanding these two perspectives, philosophical and scientific, we can hope that eventually we'll be able to use these effectively to drive innovation in computer science.